Hello and welcome back to geology. Now here I want to start talking about igneous rocks. And so the igneous rocks, like I talked about in the rock cycle, all igneous rocks share one common characteristic. Igneous rocks cool from a magma. They start off as magma and then they solidify. And either they're going to cool quickly or they're going to cool slowly, right? So we classify igneous rocks based on two characteristics. And the two characteristics we use composition and texture. That's how we classify igneous rocks. So the composition refers to the minerals. Are they mafic minerals or felsic minerals? So it's really the chemistry, whereas texture refers to the cooling rate, how quickly it cools, and maybe how viscous the rock is in terms of gas content. And so we start talking about whether the rock is volcanic, something erupting from a volcano, whereas plutonic rock cools in the subsurface. And also when we talk about composition, we're going to break out igneous rocks into having a felsic composition, intermediate composition, mafic composition, and the mantle rocks are said to be ultramafic. So remember, whenever you see mafic, we're thinking rich in magnesium and iron, so low in silica but rich in magnesium and iron. So you can see the silica valley is a little bit lower. But ultramafic, you can think of very rich. These are very rich in magnesium and iron. To understand this a little better, let's look at this volcano plutonic system over here. And so I got a little cartoon going here, and we see one of the first things I want you to show is that in this region here, we have a special name for this pre-existing rock. So note we have these layers. So this rock we call the country rock. So the country rock is the pre-existing rock. So this magma, we have partial melting from the mantle. When we talk about plate tectonics, we'll talk about the origin of magma. But small percentages, 2 to maybe as much as 10%, maybe in some cases 15%, of the mantle can melt, and we have these partial melts, and they're coming up and they're adding magma. Remember, magma is molten rock, high temperatures. They're adding magma to this magma chamber. So the magma chamber is the reservoir in the subsurface where the magma exists. So we have a special name for this rock because this magma is intruding into the crust. We call this rock down here intrusive. So intrusive rock, when it cools and solidifies, it becomes plutonic. So once it's solidified, crystallized its minerals, we call this rock plutonic. And so think of Pluto as a Roman god of the underworld, right? So at depth. So that's where we get this term over here, plutonic rock. So another term we use for plutonic rock is intrusive, because it intruded into pre-existing rock, and that pre-existing rock is that country rock. Some of this magma may go up through conduits here, and these conduits, or feeder dikes is what we call them, will feed magma to the surface, and this will be the volcanic rock. So let's put over here. And so that's extrusive rock will be volcanic. So when we go back to this chart here, when you're thinking about plutonic, that's another word is intrusive. Another word for volcanic would be extrusive, because it comes out of a vent. The key thing is volcanic rocks come out of a vent. And so when we look at volcanic rocks, we're going to see there's really two things that are going on. We're going to have some volcanic rock that explodes out. So this is going to have a high gas. So that gas expands and forces the magma and explodes out of the volcano. So the general term we have for this type of volcanic rock, we call this tephra. So tephra is said to be pyroclastic. Pyroclastic rock explodes. Think of fire. And this word here is a Greek word. This word clastic is a Greek word for broken. So this magma has been shattered, broken by the expanding gas. So pyroclastic, tephra. So tephra is anything that explodes out of the volcano. But then the other type of volcanic rock will have lower gas content, and this is going to ooze out of the volcano and flow down the sides of the volcano here. So this is going to have lower gas content. It's going to flow down here, and we're going to call this lava. So lava is going to have the low gas content tephra, the pyroclastic material, is going to have high gas content. But the key thing is both of these are extrusive volcanic rocks. They just differ in their texture. This is going to have that fragmental pyroclastic texture. Usually lava, remember, they're going to cool fast. They're going to have a fine-grained texture, small minerals. So let's look back over here. So in terms of chemistry, felsic rocks, whether they're plutonic or volcanic, are going to have high silica, greater than 65% silica. Remember, silica is just quartz. Intermediate magmas, whether they're plutonic or volcanic, will range from 53 to 65%. Mafic, like basalts, magmas will have 45 to 52% silica. And then the ultramafic magmas, like the mantle rock, peridotite, has about 45% or less. So these are going to be lower in silica. So one thing that we can think about as we go from felsic to mafic compositions, you'll see that the silica content decreases, but as you're going again from felsic to mafic, the magnesium and iron increase. Felsic rocks have low concentrations of magnesium and iron. Remember, these mafic and ultramafic rocks have high concentrations of magnesium and iron. Now, going back to our figure here, there's a couple other features we want to look at when we look at the plutonic rock. So when this magma chamber finally solidifies, and some of these magma chambers can take 200,000 up to 500,000 years to become solid. And so when it does become a solid magma chamber, the solid rock here that solidifies, it's intrusive, has a special name. It's going to be called a Pluton. So Pluton is a solidified magma chamber. If you the Sierra Nevada, there are hundreds of Plutons in there. And at each Pluton, if you can measure its diameter ranges anywhere from around 1 kilometer to as much as 10 kilometers, up to 6 miles. So that some could be quite large. But usually they're about maybe a little over half a mile to 6 miles. So they're pretty large features. And one thing that we know about these magma chambers, pretty much if you can measure how deep they form, they're usually in that 10-kilometer range. Some can get up to about maybe 5 kilometers, and that causes some other problems with big volcanoes. For example, the pretty shallow magma chambers can have the volcanoes above them can collapse down and form these giant caldera systems. And a good example of one is Yellowstone. Yellowstone is a giant caldera, and the magma is relatively shallow there. Here in California, one of the places we'll go on our field trip, if you go to the Eastern Sierra, we have the Long Valley caldera. And in Long Valley, again, that was a relatively shallow magma chamber where the volcano basically collapsed into its own magma chamber and caused a ginormous eruption, hence the word supervolcano. All right, so that's a little bit about how these, how deep these things are forming, what the rock is called when it does solidify. Now, when this thing is still molten, it's shooting magma up and maybe adding magma to the volcanic system up here. Maybe there'll be some magma that may shoot out the side here and go parallel to the existing layers in the country rock. So whenever you have magma that shoots out parallel or takes advantage of the existing weakness in the sedimentary rock, in this country rock, these parallel intrusions are called sills. The key thing about sill is that it's said to be concordant. Concordant means it conforms to existing structure there, right? But then other intrusions may be quite random and just cut across the sedimentary layers there, And so when they cut across here, like this one here, it's cutting across the layers, and this one here, these guys, let's shoot one down in here. These guys are called dikes. And here's another dike here. The dike that cuts across here and feeds the volcano, usually we call these a feeder dike. So those are some features we look at when we're looking at some of these intrusive figures. And your book has some of these as well. Let's take a look. And so in your book, you have the large magma chamber. And then eventually when that solidifies, that can be the Pluton, individual ones of these. If a whole bunch of these group together and they cover an area of over 100 square kilometers, then we call that a batholith. So the Greek word batho, or bath means deep, and remember lith is stone, so deep stone forms at depth. Small intrusions, small magma chambers that are 1 kilometer or smaller, we call those stalks, right? So that's another term. Instead of Pluton, we call it a stalk. You can see here's a discordant intrusion. So remember, a dike is said to be discordant because it cuts across layers here. Here's a sill because it's concordant. Here's another magma chamber which will form a Pluton or a stalk. And then here we have some lava, right? So one thing we don't see in this picture is the tephra that would occur. That's pyroclastic. But other things we look at, there are these kind of bowed intrusions. They sort of are going to be a sill, but they bow up and they become something called a laccolith. And then again, here we're seeing the pre-existing rock called the country rock. So here I have some images of Plutons. We're seeing a magma chamber intrusion, again, intrusive rocks. Note that there's some older Plutons that have solidified here. And then we see some sills in here, a feeder dike feeding the volcanoes. Here we see the tephra and the lava flows. And one thing that you should also note is because this magma is at high temperature, the surrounding country rock here, sometimes it's called the wall rock, is going to get burned or baked. And so we get a bake zone where we get some metamorphism, some changing, altering of the existing country rock or wall rock. And so usually we call this a contact metamorphism because it's in contact with this heat source, and we call it a Hornfels facies. So when we do metamorphic rocks, you'll see what that means. So there's our bake zone, our Hornfels contact metamorphic zone. So here is a picture of a Pluton, an intrusion of granite or granitic rock. Here's that older country rock or wall rock. And we see the baked or Hornfels contact metamorphic zone in here. And so as we're going along in here, we see now all the Plutons have solidified. Usually we say 40 or more because each of these is going to be over a kilometer in diameter, up to 10 kilometers. And so remember, they become a batholith. So when they coalesce like this, they become a batholith. And then over time, as we see erosion, we can expose these intrusive rocks, and we can see the batholith or the basement rocks here, right? So a good example of a batholith is the Sierra Nevada. So the Sierra Nevada is a batholith. So this is the exposed parts of that Sierra Nevada batholith, right? You can see there's also the Idaho batholith. Up here, mostly in Canada, we have the Coast Range batholith, which is a very large batholith. And then we have down here in Southern California that goes down into northern Baja California, and that's called the Peninsular batholith there, right? So, so again, the Sierra Nevada, later on we'll talk about how these structures form, these exfoliation domes, is because remember, these guys were deeply buried, but now they're exposed, so they're kind of stretching out into this exfoliation there. All right, so that's a little bit about intrusive rocks.